All right, thanks, Louis. Hi, everyone. Good morning. This is Derek Hengeveld. Also speaking today will be Jake Moulton. We're here to talk about Veritrek. Before we do, just a couple housekeeping items. As Louis had mentioned, feel free to include some questions as we go along in the chat function, and we will, try to respond to those as best we can, either through chat or we'll stop the presentation and provide answers. So at a high level, Veritrek is a software tool. If you're not familiar with it, basically what it does is it converts converts thermal models into a reduced order form. So just imagine, if you're a thermal analyst and you're using a tool like Thermal Desktop, basically what it does is it converts that Thermal Desktop model into a reduced order form. And the reason for that is that we can run the reduced order model much faster than we can run the fundamental or the underlying high fidelity model. In fact, with a reduced order form, we can run thousands of simulations in seconds. And so yesterday we had kind of part one of the Veritrek story, which we covered the Veritrek creation tool. Today what we're going to cover is the Veritrek exploration tool, which is basically kind of the tail end or the analysis functionality within Veritrek. On this first slide, there's a couple success stories of people that have been using Veritrek for a wide range of applications. We have NASA JPL. They're using Veritrek for their Mars 2020 helicopter. If you're not familiar with that, stick around, go into virtual session 2 here in about an hour. I'll be talking about some of the work that we're doing with the Mars 2020 program. We had ATA Engineering. They've used Veritrek successfully for design optimization. They had a CubeSat problem where they had multiple radiators and components and heat loads, and they were trying to manage all of that, trying to optimize radiator sizes. And so we use Veritrek to reduce their thermal model into a reduced order form and use that form to quickly optimize the radiator sizes. We also had Sierra Nevada Corporation use Veritrek successfully for design verification of their Dream Chaser. And then also NASA MSFC, they've been using Veritrek for a variety of purposes, one being their Lunar lander program. They use Veritrek to generate response surfaces. Before we jump into more details about Veritrek, just a couple thoughts on, or a couple slides on LoadPath, which is the parent company behind Veritrek. We're both Jake and I, we are employees of LoadPath. LoadPath is a small business. We're about 25 employees strong. We're based out of Albuquerque, New Mexico, with a couple satellite offices. We have pretty broad experience in delivering flight hardware, working on space flight missions. Of course, we work in thermal. That's what both Jake and I do. We both do thermal hardware and thermal analysis, but we also do deployable structures, structural testing, and mechanical design and analysis. Some of the things that we do on the thermal side, we provide thermal hardware. We do deployable radiators, specifically for SmallSat applications. We do thermal energy storage panels, high-K lightweight thermal straps. And then on the analysis side, we do kind of a broad range of different analysis services. We do traditional thermal desktop modeling, whether that CubeSat modeling or, there's a couple examples here where we're doing some modeling for gimbals and sequencers. So if you have any interest in any of this, feel free to reach out to us, either Jake or myself, and be happy to talk to you about that. All right, so with that, let's jump into Veritrek. What is Veritrek? If you're here before, some of these slides are going to be a little bit of repetition from yesterday, just a couple of them, before we jump into the exploration tool. But if you weren't there, this is good information to kind of give you an idea of what Veritrek is. Essentially, it's a three-step process to get you from your high-fidelity thermal desktop model into a reduced order form. So step one is you start with your model. You have your thermal desktop model. It's basically it's based on symbols and registers, and it's highly parameterized. It's high fidelity, right? We use our Veritrek creation tool then in step two to basically put its hooks into your thermal desktop model, and the creation tool then semi-automatically converts that thermal desktop model into a reduced order form. And then what we're here to talk about today is step three. So once we have that reduced order model, we then use our Veritrek exploration tool to use the power of a reduced order model to generate analyses. And we have a very quick example here, a quick video that kind of shows what the exploration tool looks like. We'll have a much longer video later that kind of shows all the different functionality. What we've done here so far is we have a reduced order model. We've pulled that into the Veritrek exploration tool. This particular model is a reduced order form of a NASA crew exploration vehicle. And so this is heavily based on syndiffluent. It includes working fluids, regenerator properties, all sorts of kind of fluid-based modeling properties. What we're doing here is we're basically changing the symbols in that fundamental thermal desktop model. Basically, every time we're moving a slider, we're changing a symbol value, and every time we're changing a symbol value, what we're seeing on the right-hand side is a change in a response surface. That's just one of the analysis features that we have available to us in Veritrek. And behind the scenes, what's going on here is that we are running 400 simulations to generate that response surface. And you can imagine trying to do that with traditional methods. Running 400 simulations is very computationally expensive, but by first converting our thermal desktop model into a reduced order form, we can generate these response surfaces in near real time. We can see we're moving that slider and the response surface is changing almost instantly. So hopefully you can start to see some of the advantage of Veritrek. You know, we can run simulations very quickly, get our results very quickly, which really opens up our analysis space. All right, Jake, we can move on to the next slide. Okay, so hopefully you've started to think about why Veritrek. Why do we want to use this tool? Well, let's kind of compare kind of traditional analysis approaches with Veritrek. And so in the upper left, we have our traditional thermal modeling. It's very powerful. We have, we can basically model most anything that we want. The challenge, though, is that a single simulation can take minutes to hours, in some cases days, to run, and so that can be that can prohibit us from doing all of the analysis that we want to do. And so in many cases, we end up doing worst case analysis or stacked worst case analyses, although maybe we would want to do more analysis. We just don't have the time to do that given the computational expense. But by converting that model into a reduced order form, we can now run thousands of simulations in seconds. And by doing that, we really open up kind of the analysis space that we have access to. And so we see some examples of some of the analysis features that we have in the Veritrek exploration tool, things like a point analysis in the lower left, 2D, 3D plots, rapid correlation, thermal model correlation feature, sensitivity studies, and optimization studies that we can, again, rely or leverage the speed of Veritrek simulations. So really what that does is it expands our analysis space and improves our understanding of our thermal systems. All right, Jake, we can move to the next slide. All right, so a quick overview of what a reduced order model is from our perspective. In some cases, people take multi-thousand node models and they reduce the node count. That's not what we're doing here. In fact, what we're doing is we are sampling and data fitting. And so we have a very simple example here that outlines that. In this example, we have one input factor on the X and one output response on the Y. And let's say the input factor is some heat load, the output response is a temperature. And so what we want to do is look at the relation or understand the relationship between an input factor and this output response. And so what we do is that we run our thermal model at a number of different discrete levels of our input factor. Let's say, again, this is a heat load. Let's say we run it at 0 watts up to 5 watts. And what we're doing is we are tracking an output response. Let's say in this case, it's a temperature. And we track the temperature of a node, for example, at each of those discrete input factor settings. And we generate these red circles, which we would call training data. And so the next step is once we generate this training data, these 6 points, we want to fit that data. And we come up with an equation. It looks very linear. So we come up with an equation y equals 10x plus 10. And so then maybe a question might come up, what is the output response at a non-sample point? Of course, if we had the question, what's the output response at a sample point, it'd be easy to determine that because we already have that information available to us. But what is the output response at a non-sample point, let's say at an input factor of 3.5 watts? Well, one thing we could do is we could go back to the thermal model. We could run that again. But again, that's computationally expensive. And so an approach might be to use this model that we've just generated. It's much faster. So we just put in 3.5 in for X, and out comes 45 for our output response. And that's essentially what we're doing. We are sampling, so generating these red circles, and then we're data fitting, so generating a fit of that data to come up with this equation or model of these relationships. Except in Veritrek, we are expanding that quite a bit. We have multiple input factors, so not just a single input factor. We have a broad range of input factors, upwards of maybe 10, 11, 12, which is really kind of dictates the computational expense of generating the reduced order model. We can talk about that later. And then we also have multiple output responses. In some examples, the Mars 2020 program, I think we generated a ROM with 36 output responses, although we've talked to people about having a reduced order model with hundreds of output responses. And it's certainly doable within Veritrek's capabilities. A couple challenges with this approach. One is that, how do you sample this space effectively? We want to, sufficiently fill the design space with a number of samples in order to get an accurate ROM, but we don't want to fill it any more than that because that adds computational expense. And so we've spent quite a bit of time developing sampling methods, which basically does all the heavy lifting for you. And then also one of the more significant challenges is how do we fit the data for a variety of model shapes. In this very simple example, the data look very linear, nice and easy to fit. But for thermal situations, obviously we have nonlinearities involved, and so how do we handle that? So we have a fairly robust data fitting algorithms within Veritrek that, again, kind of behind the scenes does all that work for you. All right, Jake, we can move on. All right, so at this point, I'm going to turn it over to Jake, and he's going to take you through how to use a ROM, and then also take a look at a demonstration of the Veritrek exploration tool.
Yeah, thanks, Derek. So in yesterday's presentation, we kind of dove into the details with how to build and test a ROM in the Veritrek creation tool. And so today we're going to pick back up that discussion with what we do with that ROM once it's built and tested. How do we use that in the Veritrek exploration tool? So if you missed the presentation yesterday, if you have any questions or are curious about some of those creation tool details, please don't hesitate to reach out to us. We can talk with you offline, address any questions that you have regarding the creation tool. But today we're going to focus on using a ROM inside of the exploration tool. So this assumes that we have already built our reduced order model in the creation tool. We've tested it. We're comfortable with how it's performing. And so all we have to do is import that ROM into the exploration tool, and we can use any of the 6 analysis features that we provide inside of the exploration tool to perform our rapid thermal analysis. The exploration tool has built-in ROM and analysis session management, so you can import multiple ROMs from multiple thermal models, be performing multiple analyses types, and we try and make that as intuitive and easy on the user as possible, kind of keep everything organized and yeah, as intuitive as possible. So now we're going to take a look at a video demo that talks about and shows how the exploration tool works. So again, this is assuming we've already built our reduced order model in the Veritrek creation tool, and we're going to pick back up this video with where we left off yesterday. We built a 6U CubeSat ROM from an underlying thermal desktop model. So we're going to open up the Veritrek exploration tool, and the first thing we're going to do is import our ROM that we created. So we simply select the ROM directory that the creation tool spits out for us. Once we import that ROM, we want to create a new exploration tool session. We'll give our session a name, and then we're going to tie that session to a specific ROM. So the ROM that we created and imported shows up in our list of available ROMs. We tie that to our newly created session, and now we can start our rapid thermal analysis. So the rest of this video just kind of briefly highlights the analysis features that we provide. This first one is our point analysis feature, which is essentially an Excel-like table that allows you to evaluate discrete point designs. And the power of Veritrek coming into play, you can adjust these symbol values on the left, and we see the output responses on the right-hand side update in real time. The second analysis feature we're going to look at is our factor sweep analysis, which is essentially a 2D parametric sweep plotter. So we can choose an input factor that we're going to sweep through on the x-axis and look at how the output response on the y-axis changes as we sweep through that model parameter. And again, leveraging the power of the ROM, we can make adjustments to our input factor values very quickly on the left-hand side, and we see our parametric sweep plot update in real time on the right-hand side. Next, we're going to look at our surface plot analysis feature, which is essentially an extension of our factor sweep analysis. It's two parametric sweeps at the same time. So we have two input factors on the x and y axes, and we're looking at one output response on the z axis. And so, we can, again, adjust values for our inputs in the input factor pane and see the output responses on the right-hand side update in real time. And we can zoom in, zoom out, rotate this surface plot around, all of that fun stuff. Next, we're going to look at our screening analysis feature. This allows a user to understand the relative impact that each input has on a given output response. So we can see what's driving our thermal control system mass, what's driving our thermal design cost, which model parameters have the biggest impact on a maximum node temperature. And so we can use this information to understand those thermal design drivers and focus our efforts on those that have the biggest impact on our output response of interest. Now we're going to look at our optimization analysis feature, which is essentially a plotter for a design envelope. So we set up two output responses on the x and y axis, in this case, a payload minimum and maximum temperature. And what I'm going to do is set up two exploration tool runs, two design options that we can compare side by side. So one is a standard nominal design, and one is an altered design with some of our LoadPath thermal control hardware. So we're going to use an APG deployable radiator for our CubeSat and include a thermal energy storage panel on our CubeSat's payload. And what we can do is very quickly interrogate these two designs with thousands of points and get these dot plot results that show our design envelope. And so we can very quickly see that with our LoadPath design, our payload maximum temperature is reduced by about 15 degrees Celsius. And lastly, we're going to take a look at our correlation analysis feature, which is currently in a beta state, but it will be rolled into the next commercial release, which should be later this fall. And this analysis feature was developed based on feedback from our customers and was geared towards assisting our customers with correlating their thermal desktop model to thermal test data. And so how this analysis feature works in this measured column in the experimental output section, this is where you put the temperature measurements from your thermal test, so the values that you're trying to correlate your model to. In this example, I want to correlate the model to be within 2 degrees Celsius with all of our temperature measurement locations. And we can leverage the power of the ROM to very quickly investigate thousands of different combinations of our input factor values. And Veritrek will sort those and organize those for us so that those input factor combinations that appear at the top of this list most closely match our measured values that we put for those thermal test data measurements. If we invoke the margin feature like we did in this example, all of the combinations that show up in this list fit within this margin criteria. So Veritrek gives us a lot of options that we can kind of pick and choose from to most accurately correlate our thermal desktop model to our thermal test data. Okay, with that, I'm going to jump back into the slides. These next two slides just kind of highlight some of the work that our customers are doing and what they're using Veritrek for. So as Derek mentioned, ATA Engineering has used Veritrek for some design optimization efforts with one of their SmallSat buses. So this particular use case, they had a SmallSat radiator that had 6 different body-mounted radiators on 5 different sides of the SmallSat bus. And they wanted to optimize the size of each one of those radiators to meet temperature requirements in a worst-case hot condition and heater energy requirements in a worst-case cold condition. So kind of that balancing act that some of you might be familiar with. So the metrics for this reduced order model, they had 6 input factors, 10 output responses, so 5 temperature values for 5 electronics components, and 5 heater energy values. Those were the 10 output responses. They ended up using 256 training runs to create their ROM, and we can see an example of one of the test result plots just to kind of give you an idea of the ROM accuracy that we were able to achieve for this reduced order model. But how they used Veritrek to perform this design optimization, they used a combination of the optimization analysis and point analysis feature. So the optimization analysis provided them with tens of thousands of data points, and they could kind of filter those data points down based off of their temperature and heater energy requirements. And they ended up filtering down to a single optimized design solution, so an optimized size for each one of their 6 body-mounted radiators that kept temperature below their maximum temperature values and kept their heater energy where they needed it as well. This slide highlights some of the work that engineers at NASA Marshall have done. They used Veritrek to build a reduced order model for their lunar lander. So they were specifically interested in understanding the design sensitivity of a heat load going into a cryo tank on the lunar lander, and kind of understand what's driving that heat load value, and understand kind of the design sensitivity involved with that. So we don't have actual thermal desktop model and thermal data available for public release to show, but we have some exploration tool plots to show for right now. So the reduced order model that they built for this use case was very small. They had just 3 input factors and 1 output response. So they were really focused on kind of understanding the sensitivity of this single output response. So they were able to create the reduced order model and obtain this reduced order model data and kind of understand the design sensitivity in less than an hour, an effort that they said would have taken several hours using kind of traditional thermal analysis techniques. So they used, as this slide shows, a combination of the screening analysis and surface plot analysis. So the screening analysis allowed them to kind of understand with the input factors they included with their ROM, which had the biggest impact, which were really driving that heat load into the cryo tank. And then they could use the surface plot analysis as well to generate this response surface and understand how the heat load could change as input factor values can vary as well. So greater understanding of that design sensitivity. Okay, and with that, I will turn it back over to Derek to take us through these last couple of slides.
Thanks, Jake. Yeah, so I think you saw in the last couple slides, a couple example use cases of how Veritrek is being applied, both by ATA, for the radiator optimization. And then so basically what those slides are starting to illustrate is that the Veritrek tool can be used in a broad range of areas within the thermal design lifecycle. And so early on in the thermal design lifecycle, that was kind of where we first thought that Veritrek would have its foothold. Early in the design, you have a lot of trades that you're trying to manage. And so by doing that rapidly, you can evaluate a pretty broad range of trades. And so that was kind of our initial thought, is that Veritrek would be very valuable early on in the design. But as we started working with customers, we realized that that Veritrek provides value throughout the thermal design lifecycle. And so as the design matures, maybe we get more towards detailed design. We've had Veritrek users use that for things such as sensitivity studies. So maybe they want to evaluate, which thermal drivers are impacting your thermal results most significantly. An example of that is some of the work that we did with NASA JPL a few years ago with their Mars helicopter. We also have worked with folks on thermal testing. The typical thermal model correlation is something that's kind of a guess and check approach. It's very time consuming. And so that's why we're building up this correlation analysis feature to help out with rapid model correlation. And then also late in the design life, we've had users use it for final design verification. So kind of a final check to all the combinations of input factors. Do they all meet our requirements? And so it's a quick way of evaluating whether or not we meet our design requirements. And then also with mission ops. In fact, if you stick around in about a half hour, I'll be talking about some of the mission ops reduced order modeling that we are doing with NASA JPL for the Mars 2020 helicopter. All right, Jake, we can move to the next slide. Okay, so with that, it's kind of the bulk of what we wanted to talk about with the exploration tool. This slide really gets towards, kind of the future development. One thing to note is that we do have Veritrek 4.0, which will be coming later this fall. As Jake had mentioned earlier, it's going to include a correlation analysis feature. So we're pretty excited to roll that out and get that in the hands of users. Keep an eye out for that. That should be coming out here shortly. Beyond that, there's always active development that we're doing. And so on the exploration tool side of things, one area that we're spending a lot of time on is uncertainty quantification. Can we leverage the speed of reduced order models to better understand uncertainties within a thermal model? And so there was some work that was done on our side. A paper was put out that looked at that. And so we basically built up a variety of ROMs and used those ROMs to essentially develop these cumulative distribution functions, which you can see in the lower left. And so if you're interested in that, reach out to us. I can get you a copy of that paper. And if you want to even talk further than that, we'd be happy to discuss that with you. Another area that we're doing some active development is reduced order models for multidisciplinary analyses. So everything in this talk really was geared towards thermal reduced order models. But the reduced order modeling approach that we're taking can certainly be applied to other disciplines. For example, maybe power systems, or maybe a structural system. And so that's something that we're going to be actively developing this fall, is developing reduced order models for multidisciplinary analyses, and not only developing ROMs for other disciplines, but how do you combine ROMs between different disciplines, and how do you make them basically talk to each other? So just a couple examples of some of the future development that that we're working on. A lot of that is based on talking to customers and understanding what their needs are. So if you do have needs that you think reduced order modeling can help you with, feel free to reach out to us. We'd be happy to talk to you about how Veritrek might be able to help. All right, Jake, you can move on. All right, so with that, it kind of concludes the talk. Just a quick shout out to the Mars 2020 team. They had a successful launch at the end of July. So, we're excited to be part of that program. We're looking forward to the landing in February 2021. And beyond that, if Veritrek is something that you feel like you might be interested in, feel free to reach out to Jake. His email is right there at the bottom. Another option is, if you do want to get a free trial in your hands, reach out to us. We'd be happy to get you a free trial. Typically, it's a 30-day free trial of Veritrek. You do need to have Thermal Desktop 6.0 or greater in order to use it. Feel free to reach out to us. With that, we didn't have anything else, and so we're going to stick around. We're going to monitor the chat feature on the live stream. So if you do have a question, feel free to just type it in the chat, and we'll be happy to answer those questions. Thanks, everybody.